everyone on this planet should have the at least the opportunity to have clean, always on energy to be able to elevate their standard of living.
As role models for future generations, we're building a world where wisdom and consciousness rise, harmonizing life with nature and all species. Join us. Together, let's create a balanced, sustainable future for all.
I've always said that there's three technologies that are going to change the world in 3 to 5 years. Well, I've said it this year, not always. So one was quantum computing. I think that's going to change everything. Two is fusion. I think that's going to help power the quantum computing and everything else, right?
Yeah.
And three is blockchain. And I know blockchain has a bad rap because of crypto and stuff, but it really is the distributed ledger transactions, i.e., the public trust ledger. And that's going to change everything because now it's going to really kind of help create a better data repository and kind of validation of information. So, and then that becomes really important when you throw AI into the mix because we're working on an idea of actually being able to validate data through blockchain. And I know we're not the only ones who are doing that, but it becomes really important because of just echoes and false, fallacies and so forth, right?
Right.
So we're trying to really take advantage of technology, community, and humanity, right? And so we use those three pillars to try to help address these things. And so looking at technologies, I focused on quantum computing and fusion and blockchain, and because those are the things I care about. And that led me to you guys. You had what seemed to be a very practical application of how you're doing it and so forth. And then just based on like reading the profiles on your website and so forth. And so,
Yeah.
as I mentioned, what we're looking to do is amplify the voices of those that are starting and getting, and kind of trying different things or trying new things and just creating different perspectives on how to solve our problems.
Yeah, and I tell you, just something that I've been thinking about a lot and wanting to act on is, fusion is criticized as, yes, it has a lot of potential, but it's going to be late to the clean energy mix. And some people say, well, that we shouldn't waste any time or money on developing it because it's going to be late. And that's for addressing, clean energy, climate change. But the reality is we need to do it because we need to address energy inequality worldwide. Everyone on this planet should have the at least the opportunity to have clean, always on energy to be able to elevate their standard of living, and because the reality is, if they don't, they're going to be doing things like cutting down forests. They're they're going to be basically vehicles for disease, and so we need to create an opportunity where everyone has a potential for a first world standard of living. Um,
it, it
so
it cuts through so many different areas, right? It's when we talked about climate action, people are like, well, climate, yeah, yeah, but it's like, but it touch, because of climate, severe weather events and so forth, you have people moving from one
right,
area to another
but
area, right?
which fuels nationalism and but
Well,
destabilizes countries and creates wars.
right, and
uh,
and that leads to poverty, that leads to
right.
lack of education, that leads and we were talking to David Dodd, and he's in the resilience and adaptation model, and he mentioned, the UN. I don't know if it was the UN, I forgot who did it, but that there is an expectation that in the next decade or so, there might be 1 billion people moving due to climate events. I mean,
Yeah,
you see
that's,
wars and people trying to absorb 300,000
yeah,
refugees. Imagine trying to absorb a billion people.
yeah, it will start wars, unfortunately. And the other thing about fusion is it's really hard, and no one has been able to get more energy out of fusion than what they've put in from the wall plug. We had a significant event with the National Ignition Facility, but that's still it's one step in the process to being achieving practical fusion. So my point in bringing this up is, as a civilization, we need to set very goals to achieve, and these are things that will keep us busy. And when we achieve them, it'll ensure our survival as a somewhat sentient species. And so we need to set these very high goals for ourselves. And the fascinating thing, so I have an aerospace background, is that we make fusion practical on Earth, and then there's the potential for fusion propulsion in space, and it basically it's like a gateway. You know, we improve our society on Earth and by achieving fusion, and effectively it gives us the keys to the solar systems and to the solar system and the stars. And it's sort of like, maybe this is the great being that controls the universe, or whatever you believe. This is a step uh, uh, for our species, and it kind of grants us access to bigger things. So
And
anyway,
and I mean, and I guess that's when I look at the potential for quantum fusion, it's never just about the practical application. It's always about the potential, right? And so, like you were saying, I know that a lot of aerospace is looking at the idea of fusion as being a fuel source for, massive transportation, like long distance travel, because if not, the amount of fuel you have to carry kind of takes away from the being
right.
able to.
Well, what I like to say is we have a clean energy problem on Earth, and we have an energy density crisis in space. We're not going to be able to travel in our solar system without fusion propulsion. With chemical propulsion, it's just not practical. So, this
And I
is kind of
know,
it's like Zephyr Cochrane in Star Trek. The guy who discovered the
oh
warp
yeah, I know
drive.
Star Trek. I
And
I didn't wear, so I have a T-shirt that says, "Oh look, it's R2D2. I loved him in Star Trek," and it's a Dalek.
it's a what?
That's
Oh,
a Dalek.
a dial. Okay. Yeah. Okay. I get it. I
It's
get
my favorite shirt because every time someone laughs like that, I know I found my people.
it. That's yeah.
So, and I can get into all that so much, but what I wanted to kind of understand is a little bit about NearStar's journey, where you guys are at. As I started looking into fusion energy plants, the energy plants, right? Not reactors, energy plants, right?
Power plant.
Power plants. Okay, power plants. I realized that there's a lot of different folks chasing that dream in
Oh
different
yeah.
ways. And so, a little bit about NearStar, where you guys kind of come from and how you ended up where you are, and then why pick the technology you picked over some of the others.
Well, I'll begin. We actually are. We actually have three approaches for doing fusion, and it's kind of interesting. I'll try and get it through really quick. First of all, my co-founder, Doug Witherspoon, um, you you dropped off. Are you having bandwidth issues, Carlos?
No, I was trying to close my blinds because
Oh,
around this time every
okay.
morning,
It gets really
The
bright.
sun really gets bright, and even with that, it's still really bright. Sorry, I'm
You're
washed
down
out.
in Florida, right?
I am, yes.
Yeah. So I'm just FYI, I'm up in Boston for a fusion energy investor conference. So yeah, so our my co-founder and our chief scientist, Doug Witherspoon, he's been developing high performance plasma guns, electrothermal guns, and high performance artillery since the early 1980s. And he's had a fascinating career. And I've known Doug since the 90s. And so being a space guy, rockets have terrible limitations. And I became very interested in non-rocket launch to space, putting things in space without using a rocket. And Doug was actually looking at a gun launch to space with a big high performance gun. And small satellites that you could put into orbit. And also he's a plasma physicist. He works on does fusion research. So anyway, I went to work for Doug, his company Hyper-V Technologies, and with the idea of, and this was in 2008, with the idea of trying to commercialize a mechanical mass accelerator called the Slingatron. Unfortunately, that effort did not pan out, and then I went to work for Doug, supporting him on his work for an earlier fusion energy approach called plasma jet-driven magneto-inertial fusion. And that's where an array of plasma guns fire fuel into a spherical vacuum chamber, and then a larger array of plasma guns then fire an imploding liner to squeeze that fuel and hopefully get it to ignite. And the plasma physics of that approach is really good. Unfortunately, as a power plant, it has too many parts, and so it's highly likely that it's not practical as it has a bunch of problems in that end, in that it has a lot of parts. Some of the plasma guns at the bottom of the sphere, the molten salt gets on them and they won't function properly. Inside a reaction chamber, it's very dirty. Things are, flying all over the place, and so it's very hot, and there's radiation, neutrons, charged particles, and so it's a very hostile environment. So what you want to do is then, because of that, you want to have an approach that's very simple and robust and maintainable. And Doug came up with this approach where you have a very long plasma gun, about 300 feet long, and it's a plasma gun made up of plasma guns. And so it's basically a plasma armature railgun. And what happens is, so there's a projectile of about 50 grams, this big, it's about this weight, and you accelerate it up to 10 times faster than a high-powered rifle bullet, so 10 kilometers a second, over 6 miles a second. And it enters a chamber, and have you seen the animation? There's an
Yes.
animation. Yeah. So, and without getting into too many details, the beauty of this approach is that it has RAM. It's reliable, available. Available means that the power plant will always be there, right, and working, and maintainable. And there's a lot of fusion approaches where the science, the plasma physics of the approach has been researched and very well understood. But unfortunately, the actual mechanics of the power plant is terrible. And it's like, you know, basically these approaches are maintenance hogs, and so it doesn't look like they're a utility will be able to reliably and economically operate them on the grid. So I mean that's kind of in a nutshell, that's basically what we've evolved to. Doug has been in this business since the early 1980s. I came on board in 2008, and we've learned a lot. And what's fascinating is that fusion has, at that time, around the early 2000s, there was no real investor interest. There was no real push for clean energy, and now that all of that has changed. And so a lot of people, other fusion companies, have been able to raise money. People that we've known for years are now raising money, and because with NearStar, we did this reset where we changed our whole approach. Uh, um, um, we're a little bit late out of the starting gate with with our competitors who are our long time friends, right? And so that's
It's
why
always a
we're
small community, right?
right. And that's why we're a young startup, so to speak. But we're a young startup with a huge amount of experience,
Right.
and it's a not to go down too far down this rabbit hole, but it's a little frustrating to see your friends building pilot plants, cutting metal, and we're just starting out. So um,
So one of the things that I saw about your approach was that it was very practical
yeah,
in the way it addresses some of the elements. I mean, I like you said, I mean, trying to heat something to 150 million degrees is no simple thing, right? Um, to get the trigger for the fusion. And I know that's what they're doing in France with the like the
either
magnetic circular kind of thing, and
right. That's a tokamak.
the I'm sorry,
That's a tokamak. Yes, that's
yeah, tokamak, yeah, and it seems really cool, but it seems very big and expensive. Um,
yeah.
one of the but it seems to be perpetual once you get it.
Well, it's the idea is to maintain the plasma in a steady state, racing around this donut-shaped uh, vacuum chamber, and then you harvest the neutrons coming out of the plasma, and that's what you convert those into heat. You boil water, make steam, and spin a turbine, generate electricity.
And
And
so with yours, you're firing off the what do you call the
yeah, we're
cartridges?
yeah. So there's projectiles, and then there's a
Projectiles.
fuel target uh, that's about the size of a golf ball, and inside that the target is hollow. It's a capsule, and there's deuterium gas in it. And what's elegant about our approach is that at the moment that the projectile hits the target, it imparts mechanically a very strong magnetic field, and that confines the plasma. It keeps it off the wall of the capsule as the capsule is imploding, and we think we'll be able to uh, uh, ignite deuterium fusion fuel. And this is this is our fuel. It's inside this bottle of water, right? I mean, look at this. And deuterium, you're in Florida, you're surrounded by the Gulf of Mexico and the ocean, and that's all fusion fuel.
Right.
And so the advantage there is obviously is the easiest fuel to ignite is tritium. Tritium is it's basically like a mildly radioactive form of hydrogen, but you have to breed it, and you have to breed it in the power plant, and so it just adds another layer of equipment, of technology that you have to deal with. And because we're trying to do deuterium, we get rid of whole breeding infrastructure for tritium, and so we shrink our supply chain issues. A fascinating thing, Carlos, is there's no such thing as clean energy. Every form of energy has an impact on the environment. The wonderful thing about fusion is that it's a minimum of impact. So
I think that's really good, for people to understand, and I and it's really interesting that you kind of bring that up. So, but I guess one of the questions is in the animation you have multiple projectiles going off, and when I saw the boxes, I thought of a railgun, right? You know, because but
Yeah,
to
it's a railgun.
normally it's magnetic when you do it that way. So, but you were saying that this is plasma, not magnetic.
So, all right, very important thing. You go on YouTube, and if you Google, U.S. Navy railgun, you'll see this railgun firing these projectiles hitting steel, and this huge
Yep,
explosion without any explosive charges. The kinetic energy.
correct.
So the Navy actually shut that program down, and the reason is that's a solid armature railgun, and ours is a plasma armature railgun, and so it's a very long gun. It's 300 feet long, and the reason for its length is that we distribute the wear and tear and the heating over this very long length of the gun, and that reduces the stress and strains of firing once a second. We could have a shorter gun, but we would then increase the wear and tear on the gun. And so it's
I
like,
mean,
it's like riding in a Cadillac with a big V8 engine at like 55 miles an hour. You've got, plenty of margin on top of that. If you hit the throttle, you'd go a lot faster, but you'd wear out the
yeah.
engine eventually.
Well, I was
So
just trying to understand if there was magnetic, if because
yeah,
like I
so
said,
let me explain. So what we're doing, it's a plasma armature railgun, and it's multi-stages. So what happens is as the projectile, first of all, we inject it into the main barrel, and then we're building up a wave of plasma behind it, and that's pushing the
so you
projectile
use,
on the barrel.
oh, okay, so it's the plasma that pushes, is not magnetic
And
resonance.
the beautiful, fascinating thing about plasma is that you can manipulate it with a magnetic field. So it's what's called Lorentz force. This wave of plasma is being pushed out the barrel through by a magnetic field, and we're building up the plasma behind it. We're increasing the plasma density behind it as we fire those side injectors down the length of the barrel. So
That is a very clever design.
yeah, that's
At
Doug.
300 feet, my
I didn't think of it. Doug Witherspoon.
well, and 300 feet sounds like a lot, but I mean, if you look at 3 Mile Island, I mean, it's
Yeah,
some of these plants are massive and huge, and so 300 feet doesn't sound like a lot of real
yeah.
estate or footprint.
So we expect that our smallest power plant would be about 50 megawatts. That's a lot of energy, and that would be a power plant that would fit in a strip mall. And the beauty of our approach is that power plant could basically be in the middle of a small city, for example, right in smack in the middle, because that's how safe it is. There's no, when the power plant is in operation, it is producing some neutrons, right? But that's all shielded. And then when it shuts down, there are no more neutrons. And
Right.
there'll be some material in the power plant that will be activated. It'll be mildly radioactive, but it's extremely safe. And to that point, the Nuclear Regulatory Commission will regulate fusion power plants differently than how fission power plants are regulated. And fission power plants they're very, very stringent regulations, and those regulations, which, are necessary, drive the cost up and reduce the ability to have these power plants distributed throughout population centers. And
Yeah, and I mean, part of it is because of the way fission works versus fusion in terms of cascading, failure and so forth.
yeah, fusion. Funny, one of the big differences between fission and fusion is a reaction that really wants to happen, right? Because you've got this radioactive material, highly radioactive material, is decaying into another material, and it's splitting apart. And if you lose control of it, if you lose control of the fuel, you can. Sorry about that. You could have a meltdown. It could actually like get so hot that it melts right through your reactor vessel. And with fusion, it's a reaction that doesn't want to happen. So if the power plant breaks, everything it just stops.
Just stops. And
Yeah.
that's one of the things that I found so fascinating about fusion, and why it also, but that's also why it requires so much effort to get it to go, because it
Yeah.
doesn't want to
Yeah.
happen.
And if it were easy, someone would have figured it out by now.
Right.
And
Yeah.
the thing is,
No.
we've only just started. And one of the beautiful things about, my competitors is there's, in the free world, there's like 46 fusion companies, and most of the approaches are different. And so we're all like, a bunch of little baby turtles that have just hatched, and we're crawling into the ocean, and you know, most of us are going to get eaten by seagulls, but a few of us are probably going to make it. But it's that very organic approach, a different approach, of different power plant concepts that's
Yeah.
important because one of us is going to figure it out. Um,
Well,
and
and I think,
hopefully it's NearStar.
I think that one of the things that's important is that it I think it all solutions that I've been looking at seem fascinating and viable to some degree. I think it's cost associated with, and to your point earlier, maintenance.
Yeah.
I mean, I was fascinated. I got excited about a report that came out, and I think it was the University of Michigan. They had done a new power coding for fusion generators, so that it actually pushed plasma back out because of the way that the electrons cool and go to the edge. This coating allowed it so that it was heat resistant and protected the
Right. Yes.
actual chamber, but then because of the way that the molecules aligned, they created kind of like this little mosaic with a little hole where the cold, the plasma molecule that was cooling the, whatever it might be, would fall into that space. But as it heated, it would push it back out and push it back into the soup, right? And so creating more efficiency, because now since you're kind of recycling, the cooling plasma back into the heated plasma, it increases your efficiency.
And uh, not to, I'm going to toot our own horn here. We don't need that technology. We don't have that problem. We're pulsed.
Right.
Plasma is extremely squirrely stuff. It doesn't like being confined. And so what we do we're firing like a piston in an internal combustion engine in a car.
Yeah.
And we just let the plasma do whatever it wants, and we're capturing the charged particles and the neutrons that it produces in a waterfall of flowing molten salt, and that waterfall protects the vessel that the reaction is taking place in. And that what that means is that we can then make the vessel out of stainless steel or steel. We don't need exotic materials. And again, that's an advantage, a huge advantage that we have. We don't, for the most part, we don't need unobtainium to develop our power plant. We can use as much as possible existing technologies.
Yeah. I mean, like I said, I've been looking into this, and some of these power plants are like Star Trek kind of, and some of them look like like I'm trying to think of the term, but the one that's like a wavy loop.
That's accelerator. Yeah,
Yes,
looks like
accelerator.
a French crawler
Yeah,
opposed
and
to a
and
donut.
I mean, it's fascinating, the idea of what it's doing and everything, but I always think simple will always win, only
Right.
because maintenance and sustainability becomes a major issue in being actually commercialized.
Yeah.
So,
And so it's like with us, what I believe is that we're not going to be first to market, but I think we're going to be the most practical. So it's sort of like, Mercedes invented the car, but Henry Ford made it practical
There you go. I like that analogy,
and
and that's
affordable.
a really it's a really good one, right? And you are kind of creating more of that assembly line kind of model.
Yeah, yeah, no, and I what I would love to see is you have factories basically all over the world cranking these things out, and we're going to need tens of thousands of them. I mean, this is a technology that could scale to meet the energy needs of the entire planet. And more, what's kind of a scary thing is, as computing power grows, we're going to need more and more power to meet all of that. And blockchain uses a lot of energy because you have to maintain the transaction, right?
Well,
So,
and that's what I was saying with like quantum computing, the amount of energy it's going to require,
right.
it's going to need a new power source.
Yeah. So, and case in point, there a guy who has a company. There's an article about a guy. He builds server farms out in like Seattle area, and a conventional server farm for like the internet consumes about 30 megawatts. Well, it's an AI server farm. He just built one, 80 megawatts. That's just one
Wow.
server. That's a huge
Wow.
amount of energy.
Wow. That's crazy. Yeah. Yeah. I mean,
You know,
and that's the thing. And I know a lot of people are also talking about convergence, right? As all of these technologies kind of start to kind of come into their own, and then they start to be kind of synthesized into solutions that kind of come
right.
together. It it all has to kind of happen, right? Quantum computing has to evolve, AI has to evolve, clean energy has to evolve, right? And so and once you actually address clean energy and you have quantum computing and AI, then it kind of goes into like the next level, right? With now you start to look at, okay, what are some of the other problems we can solve, because we don't no longer worry about energy, right? It's available. It's as you when we started, what you said is about making it more democratized in a way, right?
Right.
So it right now, when we look at climate action, when we look at what the problems are, it seems very scary. But when I started to look at what some of the solutions that people are building, it gives hope. And I think that
Yeah.
that's what becomes really important, because there is potential and hope. And that's again, the humanity of it is, we adapt, we overcome, and we keep going.
Yeah. We need to have hope.
Yeah.
And I worry about all the, young people today, especially in the United States, what they're exposed to, and just, the media, internet, and I don't want them to, shut down, and give up and just, live in a virtual world. Um,
Yeah. Yeah. No,
and
I agree.
the
I,
solutions are out. The solutions are out there, and they're worth taking on, at least trying. A story I think about, and I can't remember if it was Buzz Aldrin that said it or Neil Armstrong, but someone asked one of them, what would you guys have done if, when you're in the lunar module and you're going to take off from the moon and the engine didn't work? And the guy said, well, we'd be very busy trying to figure out what was wrong, with the idea that they weren't just going to sit there until, their life support ran out. They're going to be very busy working on solving the problem. And
right.
and that's what we need to do as a civilization, is get busy working on solving these problems. And I think we're just getting started. And we've
So
been
now I'm going to get
lazy
into
with
some very
energy.
practical questions for you, sir.
What's that?
I'm going to get into some very practical questions for
Okay.
you. I
Yeah, yeah.
love. I,
I'm
it was
enjoying this
it was
conversation.
huh?
I'm enjoying this conversation.
Exactly. Yeah. No, it's for me, it's all learning, right? Like
Yeah.
I'm just excited about learning and just seeing and you know, to think that 3 months ago I was saying, oh, these are technologies that are going to change the world, but I don't have anything. And now I'm talking to someone who's doing it. That's pretty awesome. But so you mentioned you're in Boston at an investment convention. To build one of your power plants, how much would it cost?
Well, so a little more, $600 million for basically a design that we could then hand to a company that builds power plants. And our business model is to not be in the business of building power plants, but to just come up with a viable design that we would then license to, let's say, like a General Electric, and they can go out and build these power plants. And ideally, I'd love to see the technology go to a company that literally is just, has an assembly line and is just cranking these things out because it's extremely modular. So,
Yeah, that's you know, when I said that you really are like the Model T, right? It's a great analogy because you are very modular in terms of like an assembly line kind of model. Unlike some of the other ones where it's like single unit pieces that all have to kind of be forged and everything.
yeah, and so here's another neat thing about us, and um, so the most expensive part of the power plant is the plasma plasma gun driver, like we call the driver, and the capacitor banks that provide the energy pulse for that driver. Now, they're outside of the neutron flux. Okay, so there's a shield, concrete shield, we call it bioshield. It's around the reaction chamber, and so that the driver is the most complicated part, and it's going to need maintenance, right? And because it's outside of the neutron flux, it doesn't become activated. The metal won't be mildly radioactive. And so what that means is that people can work on this equipment and service it very quickly, as opposed to having our competition has to use robots. And so these robots have to be developed and they're going to have problems. And so that's another piece of unobtainium that we don't need.
I like unobtainium. That's
I got
good.
that. I stole that from James Cameron.
Oh, nice.
Remember?
Yeah. So the other one is okay, so you're using energy to create energy, right? That's always been one of
Yeah.
the key issues with fusion. How does, I mean, are you, do you feel that this will be able to produce more energy than it's consuming in a factor that can be commercialized?
Yeah, that's our goal. No one has achieved that yet.
Right.
The National Ignition Facility basically produced more energy from the reaction that the lasers put in, but they didn't produce more energy than the energy going in to drive the lasers. Uh,
Correct. Yeah, I read that. I read that, and so it was the experiment was able to produce 3 parts for the 2 parts it put in, right? But it
yeah.
didn't account for the external factors that powered it.
And I liken it to, when personal computers came out in the early 80s, and it was like a 64K, and you could barely do anything with it. And
Hey, Commodore 64s were great. You can go on the bulletin board systems and have a great time, you know, with your 24 baud system.
yeah. But it's like any, you look at the automobile. When it first came out, it's extremely limited in what it could do, and there were no roads.
It was a horseless carriage.
Yeah, yeah.
It wasn't even an automobile, it was a horseless carriage.
That broke a lot and was extremely
Yeah.
expensive.
So, I mean, and I guess um how So let's say you got funded by the US government and they just gave you money, right? How long would it take for your NearStar to come up with its prototype, implement it, and bring in a partner to kind of develop it and experiment it?
So, well, it's going to take us about 10 years.
Okay.
And that's, that's part of sort of the human factor problem in that, our society is all about instant gratification. Think about, you know, humans don't, or corporations don't really plan further than 5 years out, and
Hmm.
so this is something that, as a civilization, we need to be thinking about, you know, we need to be thinking out 10 years or more. And I think we're starting to do that. And one of the things that's inducing us to do that is climate change, is our effect on the planet, and the fact that we're degrading the environment of this planet. Um,
Right. I mean, there's obviously the 2030 Accords, right? But then there's also the 2050. So this is more of a 2050 kind of target.
yeah, it's gonna take this is gonna take time. I mean, even if we had working power plant today, that producing them and distributing them throughout the world. I mean, it's a huge effort, but it's it's a worthy goal. It's something that we have to do. Um,
And compared to your competitors, do you feel that your timeline is faster or shorter, or like, do you think other
it's
competitors
actually
can get to
it's
market
long. It's
faster?
longer. It's longer.
It's longer.
Yeah, but it's probably more conservative. But that said, it's still very ambitious. So, and but we'll do our best. We can only try.
No, and I mean, and that's the thing is, it's I think that it's fascinating, and you're right. The society has become so Amazon in its thinking, right? It's like,
Yeah.
when can I get it, right? Um, but some things require longer term planning, and it does seem, and when people think of fusion, it's like, oh, over the past year, it's gotten a lot of attention. But some of the earliest experiments, I think, go back to the 50s.
Oh, we've been experimenting. You know, human civilization has been experimenting with fusion energy since the 1930s. So, yeah, but just, again, no one has been able to get more energy out than what has been put in from the wall plug. And
Right.
but we'll get there. I mean, it's part of what has changed now, in part in fusion research and development, is the fact that we the science of plasma physics is not complete, but we know so much more. We've learned so much more over the years. All that research since the 1930s is not a lost effort. We've built a knowledge base, right? And the other thing is we have cheap, ubiquitous, highly powerful computing power. And so plasma is very, very difficult to model. It uses a lot of computing power. Case in point, so in 2009, we bought this computer. We spent $100,000 for this computer. It was a Beowulf cluster, and it was this huge wall of computers, like desktop computers, all clustered together. And it was in Doug's office. And the computers used so much energy that in the wintertime, Doug didn't need any heat. His office was heated by CPUs, basically running. But the crazy thing is that that computer inside of 2 years was completely obsolete. And the same computing power now you can get in a laptop, right? And it's $1,500.
Yeah.
And so it's that convergence. We talked about convergence earlier. That was one of the things that's really helped us. And then there's been advances in materials, um, and technology, supporting technology that has helped moving things along.
So do you feel good about fusion in spite of people saying, that other clean energies are going to be faster, cheaper, and so forth. Do you feel good about it? I mean, I know you work at a
Yeah,
company that does it, but
yeah, it has its role. We don't fully understand. For example, wind and solar are great and they're important, and geothermal is important, but it doesn't have the ability to scale. Geothermal, yeah, we need to do it. And there's a lot of potential there, but it doesn't have the ability to be distributed throughout the world. And, not every country is going to, be able to completely power itself with fusion. I mean, some societies are, it's just, you know, uh, it's just going to be chaos. But, one of the beautiful things about having a fusion power plant is, again, you have a population center, you put that plant right in the population center. So if there's no grid there, basically, you could have a microgrid, basically. All right, and you can
that
do
kind
that
of
with
goes back to Edison's original direct electric, right?
right, yeah, yeah, exactly, but more efficient.
And doesn't kill
Um,
an elephant, right?
yeah, exactly. But yeah, so you think about, let's say, with the telephone, for example, in 1988 in India, there were 10,000 people for one phone, right? And technology has progressed, right? But do you think they've like strung wires for phone lines? No, they put cell networks out. Everyone has a cell phone now.
Yeah,
And that's
yeah.
it's so you'll be able to have highly distributed microgrids, for example, with fusion energy. And it's energy that's always on, it's always there. So you don't have to worry about the wind dying or snow covering solar panels, things like that.
And then you also made the other point, which I think is really important for why fusion energy is so important. It's not just about terrestrial; it's about extraterrestrial
Right.
as well, right?
Yeah. Um, so to give you an idea, just to put it in perspective, with chemical propulsion, that's the technology that we have today. Uh, Depending on when you leave Earth and where Earth is relative to Mars, right, it can take you 7 to 9 months one way to get there. And when you arrive in Martian orbit, you're out of fuel. Okay, you can't come back, right? So you got to refuel. You got to like crack fuel out of the atmosphere of Mars. With fusion propulsion, you can leave anytime, get there in 90 days, right? And you still have fuel. You have fuel to come back. So that's how energy
Yeah,
efficient it is, and it's faster. So it's
yeah.
energy
Wow.
dense. It's because of the energy density of the fuel. So
And then the other, I mean, for space travel, the other one that people have been talking about is solar cells.
yeah, that's they're great, and NASA's working on is building one, and they hopefully will be launching it soon. But again, it's you're limited on what kind of payload you can carry, and it'll continuously accelerate. So, but its acceleration is very slow. It's not something that, for example, you'd want to have a crew on.
Makes sense. And I think that I so I think those are things that are important to kind of address and discuss too. When we look at fusion, it's not just about the impact it has on clean energy and accessibility to power and exponential growth in power. It's also about the idea of being able to help humanity move off the planet into other
Yeah.
spaces, because that's also going to be a big problem, right? Population growth is a problem that we have to address because there's just not going to be enough land to be able to feed everyone.
Well, yeah, and I think I think there's a lot of evidence now that population is starting to level off. I mean, we're at over 8 billion people now. But yeah, there are a tremendous amount of resources in space, and yeah, fusion propulsion makes utilization of those resources. It has the potential to make that practical. Um,
So, question.
Go
Could
ahead.
fusion propulsion mm, create a commercialized. So if we needed to be able to take advantage of like asteroid mining or being able to do food centers or growth centers in space, right? So that we could
Yeah.
actually kind of expand resource capacity. Would fusion be part of that equation?
Yeah, you could fusion energy would uh, provide wonderful transportation between the Earth and the Moon because it's very fuel efficient. So you don't have to be dragging, you know, fuel around with you. And that said, even with conventional chemical propulsion, you can get around really good between the Earth and the Moon. And today, this evening, hopefully the first private lunar lander will land on the moon, and hopefully it'll be, I think, the first time that a U.S. spacecraft has landed on the moon since the end of the Apollo program in 1972.
Crazy.
Yeah, and so fingers crossed on that. So we'll see.
Okay.
So, but
So
you know, uh, there are a tremendous. The moon is 1/4 the size of the Earth. It's in an Earth orbit, right? And so, yeah, there's tremendous potential there. You can take the regolith on the moon and grow things in it, uh, and you can build very large structures that people could live in 1G environment in Earth gravity. So yeah, there are huge opportunities there.
is NearStar kind of going out there and trying to talk about what you guys are doing and why you're doing it, or are you kind of still in shadow mode? Or
No, I you know love the opportunity to talk about